All right, we're recording. So here, let me go ahead and make MATLAB bigger, especially the font. Okay, um, so all right, so and this is for anyone else who hasn't gotten to these yet. So setting f, so it's a vector for number 21. Bless you. Function handle. So handle is what they mean as the terminology that's used when discussing MATLAB to refer to a function. Um, okay. Um, a equals something if you're choosing. B equals something if you're choosing. So these those would just be numbers. Hold on. Let me start the diary here. Okay, I'll just repeat these so they go in the diary. Okay. So for instance, number 21, I could set a equals 0, b equals 1, and then my polynomial would be something like, okay, x squared minus 5x plus 6. And since this is understood by so many MATLAB functions to represent a polynomial, your graph poly, what needs to happen inside is create a vector of x values between a and b, for instance, using a colon operator, and then evaluate polynomial p at these x values. And so if you look at the list of polynomial functions that I have, okay, that would be here, polynomial functions, so you can use one of those to help you do that. And a nice thing is, with a polynomial evaluation, you can have it evaluated at a single number or at a vector or matrix. It doesn't matter. So you can do this all in one shot. So it's quite convenient that way. And then, okay, so, and once you evaluate at those x values to get your y values, then you can plot x versus y to get the graph of a polynomial on AB. Now, only for 21, not for 23, plotting for roots. And one of the polynomial functions from this list as well, which actually we've used here in class, can be used just to get for roots. But what I asked for is only to plot for real roots, because you're plotting on a real interval, so it wouldn't really make sense to plot complex roots. Now, so what you have is you get a column vector of all the roots. Now, what you can do is you can build a new vector of only the real roots. Now, there's different ways of doing that. For example, using what's covered in the text, the way you could do that is like you could have a for loop that iterates over all the elements of the roots vector you get of all the roots, and then check the imaginary part. So you can consider a root complex if like absolute value, that's ABS, of imaginary part of, and I have R of I here. This is like the ith element of a vector R of roots, if you named it that, is greater than some error tolerance because when it computes for roots, you're not going to get exact values. There's going to be a little bit of error in them. So you can't assume that it's real if the imaginary part is exactly 0. It could be some number, incredibly small number, like 10 to the minus 16th. I would recommend tolerance like 10 to the minus 8. And the way you would specify it as 1e minus 8. So that's how you specify these kind of numeric constants in MATLAB, as you also do in other programming languages. So that could be your way of determining whether a root is complex or not. And if it's real, then you can go ahead and include it. And those are ones that you would plot. And so you can do something like this. Plot, and I'll use the variable RR to refer to real root. And then you want to put it on the x-axis. So you want your y value to be 0. And then you can do something like this. Let's see what I asked for here. Oh, red circles. So RO. I mean, okay, I told you guys to look this up in the plot command, but I figured I'd give you this one. Plot as a red circle. Because by default, you give plot command a bunch of values, plots a point in the xy plane, it'll connect the dots. And you don't want it to do that in this case. You do want that for the graph. But I'm going to show you a faster way to get to real roots using what's called logical indexing. This is something I did not cover in the textbook. It's a little bit more of an advanced topic, but I figured it'd be good for you guys to know about it anyway. It can be quite convenient. So I'm going to make up a polynomial here to show you. So something that is, okay, I want something to be guaranteed to have, well, actually I'm just going to make something up. And hope it has complex roots. It probably will. So this is x to the 4th minus 2x cubed plus 3x squared minus 4x plus 5. And sure enough, oh, all the roots are complex. Well, that's okay for the sake of the example. Oh, I know what I'll do. I'm going to change the example to make it have real roots. I'm just going to add on a 0 for a constant coefficient. Oh, actually, no, I'm not going to do that. 9 minus 6. Okay. I'm going to add on a coefficient of, not to my knowledge. Yeah, we are. Yeah, thing is, we haven't been able to see in one of these monitors for quite some time. Like, it's gone on for over a week.
Do you want to see some?
I'd prefer, if possible. If you can make that happen, that'd be great.
Should be coming up under this, but it's not. There. Saying the camera's turned on, so I'm gonna call my boss and tell him to come look at it.
Okay, all right.
I'm sorry.
No problem. Okay. Now, all of the coefficients of this polynomial add up to 3. So what I'm going to do is I'm going to throw in a coefficient of -3 to make the coefficient sum to 0. That way 1 is going to be a root. Then I'm going to add on a 0. That way 0 is going to be a root. So now I have a 6-degree polynomial, and sure enough we have 0 and 1 as roots. So now the example will be a little more interesting. This one's good to know things. If the coefficients of the polynomial sum to 0, then 1 is a root. Okay, so I'll make a variable called real roots, and I'm going to specify indices in R of R, like because R is a vector of length 6, and I'm going to give it a logical expression. In other words, an expression that's only true or false that will pick out the real roots, or in other words, the roots that have negligibly small imaginary parts. So I'll do the expression I had before. Absolute value of imaginary part of R is greater than a tolerance. I'll choose 10 to the -8th. Let's see. Okay. So if I do that, I put greater than, that picks out the complex roots. If I choose less than, then it picks out the real roots. So the way this works is this is what I use for indices. All right, so absolute value of imaginary part of R is less than 10 to the -8th. So if I were to just look at this expression to see what it looks like, it's just a vector of 1s and 0s, true or false. 1 for true, 0 for false. And notice it identifies it as a logical array. So if I use, so this is another way of indexing. If you give as a vector of indices all 1s and 0s, it'll pick out the elements for which this vector is equal to 1. So that can be very convenient if you want to extract part of a vector or matrix where all of the entries satisfy a certain condition. Definitely more convenient. So instead of using your own for loop or if statement, you can always use this. All right. Now, if I go back to what I had earlier. So for graph poly, this is what you're doing. For graph function, you're doing exactly this again. But you're only producing a graph. You're not doing anything to do with the roots. It's just that now what will happen is, and I'll show you what I mean, like how you work with a function, like a more general function specified as a function handle. Okay. Well, first, any questions about this for graphing polynomial and its roots? Okay. Okay. So I'm going to make up an example here. So the @ sign indicates this is going to be a function handle. The x in parentheses means it's going to be a function of x, and I'll just make something up. Sine 3 times x. Okay. So what you can do is, so if I want to evaluate this function at certain x values, I can just do like you would write mathematically. So f of 1 or f of 0 to evaluate the function. Also works on a vector. So f of, let's say, 1 to 10. The vector values from 1 to 10, and it'll evaluate that function at all of those values. So that could be very convenient. But you have to be very careful about this, that only works for vectorized functions. And I'll give you an example of what I mean about a function that is not vectorized. Because a function like the elementary math functions, sine, cosine, square root, exponential, ones that MATLAB provides, they're all vectorized. So if you pass in a number, vector, or matrix, it doesn't matter. it will evaluate the function at each element of whatever you give it, and you'll get the same kind of object back. But other operations are not. So I'll make up another function, g of x, and I'll make it a polynomial, like, well, no, actually I'll do a rational function. 1 over 1 plus x squared, which will be of interest to us for other topics later. Okay, so I can go ahead and do g of 0, no problem. But as soon as I give it a vector, let's say a 1 to 5, it's not going to like that. Because these operations, dividing or squaring, can't use those on vectors. Also, if I pass a matrix, it'll do it, but you might not like what you get because it's not. It's gonna, for squaring a matrix, it'll do matrix multiplication, not component-wise squaring. Can anyone tell me how I can modify this so that it will work if I give it a vector? What do I do to make an operation component-wise that normally isn't? We talked about this before. Yes, a dot. So you need a dot for the division and a dot for the squaring. And then it'll work just fine. So something to keep in mind about making functions vectorized. For the sake of a problem, number 23, I'll let you assume that the function is vectorized because it's very easy to make it that way. Otherwise, you need to use a for loop to evaluate your function at all of the x values you have between a and b. So then you have, once again, a vector of x values, vector of y values, then you use that to produce a graph. Okay. So if I had my function graph func handy, which I don't, unfortunately, I would do like exactly this. And then, so then you, like before, make x values in 0, 1. You plug into f, and then plot your. Whoops. Okay, I don't have that function here, so it's going to yell at me. But that's your to-do list. What?
I was making it harder than it
Oh, okay. Well, pretty much every student does that on every problem ever. So, especially in math classes. So, okay. What else you got? Anybody? Nothing at all? You're just sailing to completion? Okay. Going once? Going twice? Okay. Oh, did you have something? No? Okay. Because if I see assignments where the hard ones are just given up on, it's really going to tick me off. So just so you know, because I can understand if I'm assigning 25 of these things, and you might think, okay, well, not doing one is not a big deal, and I suppose in the whole scheme of things it would not be, but I haven't told you guys how much these things are worth, and there's a reason for that because I want you guys to make a good effort on all of them. Something to keep in mind going forward. Okay, so, but we still have plenty of time left, and even though I am going to talk about other things, if you change your mind and have questions about anything, or definitely if you need to, hit me up later. Okay. I should mention that the second assignment is posted. Okay, I'm always going to put the most recently posted assignment on top on the assignments page. So chapter 2, which I'm going to start talking about today, and then we'll also spend all of next week on. Now, as I mentioned before, there's a lot of exercises here. all the explorations into 2 sections. There's these concept checks, and then okay. All right. So the explorations you're used to, like like for a MATLAB assignment, but at the end of each section, you'll have these to answer. You know, your true, false of reasons, a few of those, and then other very short answer. Basically, did you read the dang text? That's what this is about, and this is what my intention is. What I expect you guys to do is really go through it, and as you come across places where you're told to try something out in MATLAB, then you really should go ahead and do that, and that's something that gives you a better feel for material instead of just what you would get just from reading it. And then, especially for this second section, computer arithmetic, there's 19 explorations here, and then the concept check sections, and again, a lot of things about definitions, just so you know the lingo, so that way, and what I expect you to do between now and our next class on Tuesday is read through at least section 2.1. So that way, when I'm yammering about it in class on Tuesday, you'll know what I'm talking about. And I'm not going to take the whole 35 minutes just to give a straight lecture on it. By working with it yourself, both before as much as you can, and also after class, you'll understand it that much better. That's the intent. And then I have 10 exercises, but I thought I'd show just a little bit of mercy and only assign 6 of them. I figure you still have enough to do, but you also will have just shy of 3 weeks to do it. I'm reminded of one of my favorite where did it go? Okay. One of my favorite internet memes, actually. That horrifying moment when you're looking for an adult but realize you are an adult. So you look for an older adult, someone successfully adulting, an adult to your adult. And it reminds me of my own horrifying moment when I realized I am the adult to your adult. So really one of the points of one of my intentions with this class is not only to teach you guys numerical analysis, but certain fundamentals about adulting. And what I mean by that is, like, for instance, with this assignment right here, there's, for all practical purposes, oh, by the way, I could have also said for all intents and purposes, not intensive purposes. So you'll also learn a little bit of English in this class. For all practical purposes, there are, probably in your mind, a zillion problems that I've assigned. There are roughly, 33, 39, 61 problems. Now, some of these will be extremely quick, thankfully, but the point is there's a lot. So, I shouldn't have to divvy these up into how much I'd expect to have done by at various junctures between now and September 19th. I should also tell you, though, it'd be pretty irresponsible of you to wait until like September 17th to get started on these. It's up to you to learn how to be less short-sighted than the average bear and plan how you're going to get all this done in a reasonable amount of time instead of letting it wait. Because also I'm going to be covering these things, some today, then next Tuesday, next Thursday, not the following week because that's when I'll be gone, and a substitute will be starting the next chapter, and basically just distribute the pain over these 3 weeks in a reasonable way, so that you're not spending too much time on it. You don't have to come up with allocate some huge chunk of time on any one day to get it done, because what happens what happens in these classes, and I've seen it in other classes that I've taught, when it comes around test time or due date, that's when all the effort is invested, and then the thing is done, whatever it is, and then you guys move on and dump that knowledge, and it's gone. What I'm aiming for is at least a certain level of saturation all semester long, and that's how these things stick. Also, how I expect you guys to go to how to make use of a textbook, and in fact, I even have in the preface how to use this book. Please follow that. I've seen instances based on questions that I get from several of you that the various text in between the explorations is not being looked at as closely as it should. There are a lot of helpful tips in between. I know the temptation is, okay, I got to get these done. I'm just going to look at these and see what I need. But just because there's not some immediate hit to your grade doesn't mean that it's not important. Doesn't mean that it isn't helpful. And if I'm pointing you to that, there's a good reason. So the goal is to structure the activities in this class in a way that will help the material stick to a greater extent than it has in other classes where I've followed the usual model, where I think what we all do in whatever class it is in this department, no matter who's teaching it, of lecturing, a few homeworks, test, wash, rinse, repeat. So it's important to keep these things in mind, that I'm telling these things because it's going to make things easier in the end, in terms of being prepared for when you are really on the spot during tests. Okay, now, because what I'm aiming for is the level of mastery that I know you guys can achieve. I mean, I've known several of you from prior classes, and even the ones that I don't, that you wouldn't be here if you weren't capable. And my goal is to find new ways, try new things, to to give you a chance to see. Whoa. Okay. They're trying to make it rain or something, but that's actually possible, because I remember when I took this class as an undergrad, it was offered by the computer science department. It was called CS 414, and apparently it was a class that everybody hated. The math students hated it because there was programming involved. The computer science students hated it because there was math involved. There was something for everybody to hate. And I was told that there were T-shirts out there saying, "I survived CS 414." I never actually saw one, and I did not need one because I thought it was the best class ever. But that's why my fellow students hated me too. So it didn't help that they were all like juniors and seniors like you guys are for the most part, and I come in as a sophomore and I blow them all away. But what was I supposed to do? So it creates a different sort of challenge than what you see in other classes, like the other reviled classes in this department, like real analysis or modern algebra. So it doesn't force you to adjust your way of thinking, but all too often the thinking in math classes in general is, okay, here's this problem, I got to go ahead and get it right. What's the approach? What's the algorithm to follow? Give me the right answer. Done. Move on. And in a class like this, especially because it's the nature of a field, really, what you guys need to learn is not just about succeeding, but also, I like to say, having a constructive relationship with failure. In other words, bang your head against a wall and responding to it in the right way, and that is, which means figuring out what you need to learn from that, moving on, and finding ways to succeed from there. It's all about the recovery, not getting it right the first time. I don't expect any of you guys to get these things right the first time, especially in MATLAB. You're going to make a zillion mistakes. In fact, that's actually part of a process. Even now, after 20-something years, I write some code for whatever algorithm, and then I'm going to run it for the first time. Like, okay, let's get all the stupid errors out of the way. Like having a bad index or an undefined variable, things like that. And then once I get those out of the way, it at least runs to completion. It's like, okay, now let's find the real substantial errors, which, as I mentioned before, always turn out to be something that I should be embarrassed about. But not really, because it's just part of a process. And like for instance, what I've noticed in any class I've taught here, when I give a test, or actually even if I'm proctoring someone else's test, students here give up so quickly. Like after 30 minutes, they're out. Whereas other schools, they would stay till the end of the time trying to get every point they can. And the thing is, being successful comes from, not from learning how to get things right, but learning how to recover from getting things wrong. And that's a mindset that hasn't really taken hold here among students at USM and really needs to. And that's why I want to see more people asking questions, not giving each problem at least a good try, because that's what success is. And so when I don't see as much effort as I should, or disengagement, that's the wrong path. I know students are always concerned about, if I'm going to think that they're stupid or something like that. No. I mean, every professor is supposed to say that sort of thing. There are no stupid questions, except that I really mean it. So that's something to keep in mind. Okay. Now, so one thing I wanted to mention about MATLAB is, okay, hold on. I don't want to be distracted by whatever Dr. Schroeder wants. Okay. Now, one of the prerequisites, technically, for this class is familiarity with programming languages. As a math major, you all have to take CSC 101, C++. Not all of you may have necessarily taken it yet. But I want to get a feel for what, I know there's some variation in programming experience in the room. So how many of you have dealt with languages other than C++? Like in your case?
Well, I took Sage.
Oh, okay, Sage 305. Okay, Fortran. Okay, I'll come back to that later. Jesse? And R. Okay. Any other languages by anybody? Okay. So we've had some. Now, did you deal with Python in 305, Jesse? Okay. Yes. So Sage built on top of Python, so you definitely know Python syntax. Fortran is a very important language to know for numerical analysis. And so is Python, and certain libraries that they have. So MATLAB is technically what is known as an interpreted language, as opposed to, for instance, C, C++. I kind of lump those in together. Fortran, examples of compiled languages. I tend to think of Java as closer to, it's kind of depends on how you look at it. Personally, I think of it more as a interpreted language because even though there is a Java compiler, it may not necessarily produce machine code. It's meant to run on what's called a Java virtual machine that executes the instructions. So MATLAB, so whatever code I have in my whatever code you have in your M files, what MATLAB will do. So for instance, okay, well actually this is stuff from research, but the point is it's an M file. What MATLAB will do, it'll read the text of this M file, it'll analyze its syntax, and then it will execute the instructions itself. So MATLAB is a program for doing that. MATLAB is serving as an interpreter. By contrast, code that's written in C or C++ or Fortran, actual compiled languages, you run it through one of the compiler for that language, like GCC, or of a compiler that's built into Visual Studio or whatever development environment, and it generates actual machine language that's run in hardware, which is a whole lot faster. Now, MATLAB is kind of a mix in a way because MATLAB has like the lowest level routines, like matrix multiplication or solving a system of linear equations, uses a uses, I've almost embarrassed myself by forgetting the name of a library, and in my field I really should know it. Uses LAPACK, which is a library of linear algebra routines that is written in Fortran. So there's a mix of both interpreted code and compiled code. And MATLAB didn't always use that. Like about 10 years ago or so, it switched to using that for speed. MATLAB also tries to generate machine code from your M file to make it faster. So because the difference between the speed of interpreted code and compiled code is so vast that MATLAB has to go out of its way to do anything it can to close that speed gap. And it's actually come a long way. Now, unfortunately, one of the commands in MATLAB they used to have is called flops. Flop is short for floating point operation, so an arithmetic operation. And so you could type flops at the prompt. Now, if I do it now, it's not going to know it. Yeah. So, unfortunately, if you have a super old MATLAB, it'll tell you how many flops or arithmetic operations you performed during your session. So I would do that after a while when I was a graduate student, and so I've done literally 1 billion flops or something. I'm like, wow, I was really productive. And if you didn't do anything, it would actually say, like in words, no flops or a single flop. But when they changed to LAPACK, they had to get rid of that command, so that's unfortunate. Although one command that's persisted is Y. Type Y at the prompt. It'll create a random phrase to answer your question why. And there's certain words or phrases that'll keep popping up again and again. Yeah, so I'm not sure who the bald and tall mathematician is supposed to be, but okay. That's really weird. Okay. That's probably the weirdest, kind of creepiest one I've seen. I better stop doing this. Okay. Yeah. Oh, and sometimes it could produce a run-on. Yeah. So, okay. No more of that. So there's a Y command, there's a what command, there's a who command. I think there's. Oh, okay, that's part of Simulink. So I don't think there's a how. Nope. Yeah, I was waiting for that to. Yeah, that popped into my head too. Okay, so all right. But the thing is, the way MATLAB is used, whereas other languages like Fortran or C++ or Python also are very important in scientific computing, the reason why I do a lot of work in MATLAB is for, okay, so MATLAB is best for prototyping. In other words, proof of concept. Whereas Fortran, so like if you want to make something into an actual product, especially or even if you want to put out something publicly for other people to use, it really is best to implement it in like a real language, like Fortran. And I would recommend for scientific computing, Fortran, even over a language like C or C++. I mean, they can be quite efficient too, but not as efficient as Fortran for mathematics, maybe for other things. Like if I've come up with an algorithm, that's really where my focus of my research is algorithm design. So then if I've designed something like on paper and I want to try it out, then I write a MATLAB program to do it because it's so easy to get it up and running. Like you don't have to worry about declaring your variables, defining your classes like you would do in C++, and also being able to work with vectors and matrices so easily compared to other languages. I could have something up running very quickly, much more so than if I were to try the same thing in Fortran, even though Fortran has as many libraries out there that I could take advantage of. Because any of those routines, like solving a system of linear equations, multiplying matrices, I don't have to write those whether I'm using MATLAB or not. There's third-party libraries to do those things for me. And once I see that the algorithm is sufficiently fast or sufficiently accurate, then if I had the time or the inclination, I could convert that code to Fortran, for instance, and that's something that I could put out there for I would release in the public domain for other people in my field to try out and have a maximum speed. So each of these languages has its purpose, and I say I don't have time or inclination. Like if I had a student who was particularly interested in the coding aspects of things, then I would have them take some algorithm, whatever the algorithm was designed, and do a proper implementation of that in that language. Okay, so I just want to give an idea to all the roles that the different languages play. But there's a lot of arguments back and forth about which is the best language, and really there is no clear winner, just because all these languages are worthwhile, and including other languages that are out there that I haven't mentioned, like Julia, which has some similarities to MATLAB as well, and something I should learn one of these days. Okay. Now, all right. And yeah, it's good that computer science department here still offers a Fortran class. I don't think anyone's ever required to take it. Actually, I think if anything, a math major should at least allow it as an alternative to CSC 101. Not really a big fan of CSC 101 anyway. What?
The Fortran class made a lot more sense to me than CSC. But I didn't take 101 here. I took 102 here.
Oh, okay.
Yeah, I liked the Fortran a lot better. It made sense.
Okay, well that's good. Well, it might probably would give examples that are more relevant to a math major. We have some programming classes here, like we're working on having something at the graduate level. Like Dr. Perry taught one last spring for the first time, and maybe that's something we want to offer more often, where we're specifically catering to mathematics applications, where CSC 101 doesn't do that. And I like the idea of coming up with our own class for undergrads, but that there's certain problems with doing that. Now, actually, one thing I want to try here. Okay, there's a nice little demo. Let's see. I'm reminded of at another school where they actually did offer a MATLAB class for undergrads with, and the idea is really to teach them programming with mathematical applications in mind. And this is like early career undergrads, like freshmen, sophomores, and I think personally I'd love to have a class like that here. And I'm going to do an example that actually came out of a class like that and even led to a publication. So, and I should be able to remember how to do this off the top of my head. Okay, and this is from it was Cornell University. Computer Science 1 was the class. So I'm going to make two vectors. Well, I'm going to pick a value of n, the number of points that I'm going to have. I'll just say well, let's say 100. And then I'm going to make two random vectors, one of x values, one of y values. And then I'm going to start a loop, an infinite loop. And I'm going to plot these points into plane as blue circles. The default color is blue, and the O is to make it a circle. Okay. Then the next thing I'm going to do is I'm going to take the midpoints. So I'm going to have a whole bunch of points in the plane, and I'm going to take the midpoints of neighboring consecutive points. So in other words, I'm going to take neighboring x values and average them, neighboring y values and average them, and I'll make it periodic. So like I'll also take the average of the last x value in the first and the last y value in the first. So what I could do is for the x values, I'm going to take, and this will give you another example of indexing. I'm going to take the x's from 1 to the second to last. So 1 colon n minus 1. So that's everything except the last element. Plus, starting from element 2 all the way to the end, over 2. So this will take the midpoint of all consecutive x values. Whoops, I forgot the x. Where it's circulant, like the last element loops around to the first. And then I'm going to do the same thing to the y values and take their midpoints. And when I plot, I'm going to put a pause in here because otherwise, in a loop, everything will flash by too quickly. You won't be able to see anything. So it'll wait for me to hit a key before it continues. So we plot, take midpoints, repeat. Okay. So now I'll go ahead and do this, and hopefully it behaves like I expect it to behave. Well, I'm going to make sure I don't have any figure windows open from before. Okay, good. Now, what will happen is, as I hit enter, and nothing unusual seems to be happening to these points, although one problem is, notice that y scale and the x scale are shrinking. Before, everything was between 0 and 1. So what's happening is, if I interrupt this, and I'm going to change the axis limits, I want the x values to go from 0 to 1, and the y values to go from 0 to 1. So it's minimum x, minimum y, maximum y. And I'm going to run it again. And what happens is, it's slowly but surely collapsing to 0. But, so what I'm going to do is, I'm going to normalize these vectors. So instead of having them collapse to a single point, which is not going to be very interesting, I'm going to make each of these a unit vector. So x, I'll divide by its norm. Norm is just the Euclidean length. In other words, the square root of sum of squares. So now both x and y are unit vectors. And that way I won't have to change the axis limits. So now I'll go ahead and run this again. Okay. Now, if I let this keep going long enough, the points are all about similar magnitude, just because the number of points is not changing. Okay, something. Oh, I see what I did wrong. Who can tell me why it still collapsed to nothing? What did I forget to do? Nope. I have to normalize again. After I change the points, I still need to normalize them. Okay. So that way it's always, the x and y coordinates always make a unit vector. Okay, my bad. Okay. All right, that's more like it. Because now the magnitude is pretty much holding steady. Now we're getting some unusual behavior here. Although, this is... Some, it still bugs me why that's happening. Okay. I want to make sure I still have a correct size. Oh, I'm losing a point every time. That's why. Okay. So, what I need to do is, yeah, I need to make, I have 100 points, n points to start off with. I need to make sure I still have n after I take midpoints. So, so what I'm going to do is, for these midpoints, I'll take first just plain x, so all the elements from 1 to n. And then what I add them to are 2 all the way to n, and then going back to the first element. So that way x1 is added to x2, x2 is added to x3, and so on, but xn is added to x1. So, yeah, you're seeing me screw up royally. So this goes with what I was saying earlier about my constructive relationship with failure. So, I'm walking a walk here. Okay, so now, wait, that's 2 colon n. I want all the indices. Okay, so now the vectors will stay the same length. Okay. Okay. Now I finally have it right. I have to let this run for a while, but keep in mind, the points chosen were completely random. And yet you see a certain order happen to them. It's taking a long time, but undeniably it's happening. But you're getting a coherent shape out of them. And this little kink in the middle here is going to eventually come undone. Okay. Yeah, it's getting there. Now, I'm hoping that within a reasonable amount of time, this will actually converge to what I know it's going to converge to, which is why I'm doing this example in the first place. The points, notice, they don't appear to be evenly distributed along this curve, but in time that will happen as well. And this is going to take longer than I want, unfortunately. But the thing is, if I were to stop this and do it again with, again, completely random points, we're going to see the exact same thing happen. And so when the professor at this class at Cornell, who is Charles Van Loan, who was actually, I had him come here 5 years ago to give a talk, and he presented this. So he was actually surprised when this happened in his class. So he wanted to look into it. And it turns out that you can actually prove that if you take these random points, you keep taking their midpoints, as long as you keep the magnitudes constant, so that's why to normalize them after every step, then the x and y coordinates of these points will eventually converge to an actual ellipse. Not only that, the ellipse is going to have this 45-degree angle tilt to it. You can also figure out various parameters of the ellipse, like the major and minor axis. So basically, like the equation of the ellipse. And this all comes from, it's actually numerical linear algebra. That what happens is you can show that computing the midpoints amounts to multiplying your vectors of x's and y's by a matrix. And using properties of that matrix, you can figure out why it's going to converge to what it is. And now we see that at last it's an ellipse, so I can stop this dang thing. Now, this relates to something else that is a bit more relevant to your daily lives. Okay, and I can find a link later for like when he gives a presentation about that and how now the linear algebra involved is a bit more advanced than what you see in 326. It's actually something that I will cover more in the second semester of this sequence. But another example of the same kind of phenomenon is if I make a matrix, I'm going to make a random matrix, let's say 5 by 5, and I want to make it so that the row sums are equal to, no, actually the column sums are equal to 1. Okay, so what I'm going to do is I'm going to divide each of these, and I have to keep in mind that when I'm up in front of a class, or actually when any professor is up in front of a class, their IQ plunges by like 50 points. So I'm probably going to get this wrong again, but okay. And I wasn't planning to do this today. Okay, so I'm going to take the sum of the elements of A, but it's not all the elements. It's actually, these are the column sums. Okay, so then what I'm going to do is I want to divide the columns of A by their sums so that the columns will all sum to 1. So I'm going to, I'll explain what this is in a moment. Okay, so S is a vector. Diag S is a diagonal matrix where the elements of S are placed along a main diagonal. If I divide this, it really means multiplying the right by the inverse of this matrix. So it's dividing by those diagonal entries. So now, if I do sum of A, I get 1s. All the columns sum to 1. Okay, now I'm going to I need to check so I make sure I did this correctly. I need format short for this. Okay. All right, this will work. All right, so here's my matrix. Now, what I'm going to do is I'm going to make a random vector of length 5 that I can multiply this by. Okay. And then I'm going to keep multiplying this vector by A. And then I'm going to normal, and I'm going to make the, actually I want to make the elements of a vector sum to 1. Okay, so now the sum of all of these elements are 1. Now, the reason why I do this is, think of the vector x as probabilities. I can also think of the matrix A, each of these entries, as probabilities. So all between 0 and 1, but the sum of all probabilities is 1. So in other words, it's all the possibilities are covered in each case for each column. So if I go ahead and multiply A by x, and then keep the entries summing to 1, and keep displaying the vector, what's going to happen is, actually it happened rather quickly, only a few iterations. Actually, if I keep going, you'll see there's some change, but the point is, it's still converging to a given vector. And I'll explain what it means in a moment. But if I do the same thing with a matrix, I don't want to overwrite A. So I'm going to save A and B. And if I look at b squared, okay, and then keep taking powers of b, say b to the 10th, b to the 20th. Notice, what do you notice about the columns? They're all the same. They are also the same as this vector that it converges to. Now, what does all this mean? So let's suppose that I'm going to give some interpretation of this now. Aij is probability of navigating from web page I to web page J. So we're in Google land now. This is giving you an idea as to how very rudimentary idea of how Google searches work. So imagine a matrix representing the entire index portion of the World Wide Web, where you have these probabilities. Now, a lot of the entries in the matrix would be 0 because there's only, for any given web page, there's only linked to relatively few pages directly from there. Now, if I take a to the n and look at the ij element of that, that is a probability of navigating from I to j in n hops. So you start from page I, and click on a link to go to another page. Click on another link to go to another page from there. So n clicks all together. That's a probability of going to that page. So what happens is, as I take the limit as n goes to infinity, you're getting a probability of going to any page ever. And that's why the probabilities in each column are the same. And and also the same as this vector. The vector x is called an eigenvector of a matrix A, and the eigenvalue it corresponds to is 1. Has anyone even seen or learned about eigenvalue or eigenvector in any class in this department? Okay, 326, I hope? Okay, because I know they always intend to cover that. Whether they actually do is another question. And it doesn't seem to matter who's teaching it. They don't normally get that far. Okay, so anytime you execute a Google search, what Google is doing is working with some matrix like this of probabilities, and computing this eigenvector, and then what they do is they add a matrix to this matrix probabilities called a personalization matrix to try to personalize your search results based on, for instance, your previous searches. But they're very secretive about how all this works. And so the whole idea of repeatedly multiplying a matrix by a given vector repeatedly and seeing what it converges to, that's what happened. It's called the power method. And that's what actually happened in this example with the points, the random points. And what he converged to was describing in polar coordinates the points on an ellipse. The same idea is used by Google in their searches. So this is like linear algebra in action, if you will. But this is why MATLAB was actually invented back in the 80s by Cleve Moeller, who was substituting for my advisor, it was Gene Golub, at Stanford for the numerical linear algebra class. He wanted to make some software for students to experiment with all these algorithms in, and so he created MATLAB, and then later MathWorks was formed, and so on. So out of this kind of the power method was only developed probably around the 60s or so, but now we see 40 years later so much more useful for Google. So this is an example of how the kind of behavior that happens in these numerical methods that could be quite visually interesting, but also has some significant applications. The funny thing is, founders of Google, Brin and Page, Sergey Brin and Larry Page, they took this class, the counterpart to this class at Stanford. I've taught that class, but I didn't have them. My friend Margot Gerritsen had them. Apparently, they're pretty obnoxious in that class, just like they are in real life. But hopefully they learned something from it that helped with their algorithm. So okay. I meant to start talking about chapter 2 today, but actually it's kind of preferential that I did not. But I am going to talk about it, section 2.1, error analysis, starting on Tuesday. So, and it's about certain essential concepts like absolute and relative error, how we measure error, how we try to analyze the accuracy of general algorithms. And so what I need you guys to do, after you finish this first homework, is look at this section, do your best, so your first understanding and trying the explorations, and then we can use class time on Tuesday, the whole class time, to talk about them and make sure that any rough spots are smoothed out. So, yes. Oh, well, preferably by email, but yeah, well, any M files and a diary. And if you have something else written, like on paper, if you do, you may not. So it's not something I'm actually picky about. I just want to work. So, okay. Yeah, but I'm not going to. I'm going to be soft about the deadline. So.